line integral example. And in physics, we like to think of this in terms of work, because work is the line integral of f dot dr along some path. And so there's a lot of tricks here and a lot of cool things, and we're going to do this. So I have a make-believe force. Here's my make-believe force. The x component of the force is y, the y component is 2x, and the z component is 0. And then I want to go from A to B, where A is at the origin and B is at the point 1, 1. 1, 1, 0. Okay, fine. But I want to do this along 3 paths. So the first path is just straight there. The second path is along the x-axis and then the y-axis. And the third path is this parabola, y equals x squared. That's the path. There's a whole bunch of stuff to do here. I'm just going to go ahead and start with going along the straight path. I'm going to do the line integral. After that, I'm going to do it in Python. But before that, I want to show you what this field looks like, because I think it kind of helps to visualize the field, and sometimes that's kind of hard. So I've already created this program, but here is a quiver plot in Python, and this you can't do this in GlowScript, Web v Python. You can't do that. So I'm not going to go over all the details. Let's see. Wait, make it a little bit bigger. Is that better? Okay, so let me just really quickly. So you got to import numpy and matplotlib.pyplot. Then I make all my x and y values from, I'm making them from 0 to 1.2, and I have 20 items. And then I just calculate my x component of the force, my y component of the force, and then I plot it. And here's what you get. So at the origin, x and y is 0, so the force is 0. And then they increase as you move out. So it's got this little weird pattern like that. Now, is it conservative? We'll find out. Okay. And no, it's not. Spoiler alert. Okay, so let's get back to, that's a little crooked, the paper. I'm going to do it by paper first, and then I'm going to do that first one in Web v Python. So just hold on. We got a lot to do. Okay, so the first thing is we're using Cartesian coordinates. In Cartesian coordinates, I know the vector f. I need the vector dr. So dr is going to be the vector dx, dy, dz. Okay, so don't try to incorporate the path. Okay, the path is not incorporated in dr when you're integrating. The path is incorporated by the limits of integration and other things. So that's it. If you're doing Cartesian coordinates, you're doing a line integral, that's your dr. So we can go ahead and do, it's pretty easy, f dot dr is just a scalar function, right? So it's going to be y times dx plus 2x times dy plus 0 times dz. So that's that. Okay. So now I want to integrate. Now I'm going to do this one 2 different ways, and the other ones I won't do. So let's do this. I'm going to call it work because it looks like work. So work is the integral from, let's split this into 2 pieces. So I'm going to say y dx plus the integral of 2x dy. Now, this is an integral over dx, so I need to know I'm going from here to there. So this is x equals 0 to x equals 1. This is y equals 0 to y equals 1. And again, that just happens to be the point 1, 1. It doesn't have to be. Because that's an integral, my integration variable is dy, so I'm integrating over dy. Here I'm integrating over dx, so the integration variable is dx. Okay, now I have a problem because I can't integrate either one of these. I can't integrate this one because it's got a y in there and this has an x. So I need to get rid of that. So I can get rid of that x and the y in these 2 equations by using the equation of this line, right? So if I wanted this path, what's this path? Well, it has a slope of slope equals 1, right? Because I go over 1 and up 1, so the slope's 1, and the intercept's 0. So I could say y equals mx plus b equals x, right? Because m is 1 and b is 0. So if y is equal to x, right here, instead of y, I can put x. So I can say 0 to 1, x dx, plus. Now right here I have x, I can put in y, because x is equal to y. So 0 to 1, 2y dy. Now I can integrate both those. So if I integrate this, I get x squared over 2 from 0 to 1 plus y squared, excuse me, over 2 2y squared over 2 from 0 to 1, and this is going to give me 1/2. That one's 1/2 minus 0, and this is going to give me 1 minus 0, so plus 1. So I get 3/2 joules. Okay, now let's do it again. I didn't have to do that. I didn't have to break that into two integrals. So let me start back with f.dr. So I'll write it right here. Work equals the integral of y dx plus 2x dy. Okay, so the other way, I can just switch it all over to x, right? Because remember, the equation of my line is y equals x. So I can get rid of the dy. I can say, if I take the derivative of this equation, it's going to be dy. I have to take the derivative of the other side is dx. So dy is equal to dx. So instead of this dy, I can put dx. And then instead of the y right here, I can put x. So I'm going to do all in terms of x. I actually could do the whole thing in terms of y too. So I can say x equals 0 to x equals 1. That's 1. So that's y, I'm going to put in x, dx, and then plus 2x, and then instead of dy, I'm going to put dx. So now I can factor out the dx, and I get 2x plus x, so I get the integral from 0 to 1 of 3x dx is going to be 3x squared over 2 from 0 to 1, 3/2 joules. Same thing. Okay, so now let's do this in Python. So in Python, we're actually going to break this into finite steps, which we don't have to do. Okay, but let me just show you what we're going to do. The first thing, I have my point A and my point B. And I'm going to actually make those spheres so that we can see it. And then I can find this distance. I'll call that, I guess, S, the vector S, which is the path from B to A. Now I can find the vector dr is going to be S over n, and where n is how many pieces I want to break it into. Right? So S is just going to be the vector, let's call this B minus A. That'll give me the direction, and then I divide it into pieces. Now I have step sizes where I'm going to move in the right direction. I can move my point. What I'm going to do then is to take my force at the beginning of the interval, and I'll assume it's constant over the whole interval. And then I'll just do delta work is f dot dr delta r. And you'll notice here that in this dr, it's not dx, dy, dz. It is the path. I am looking at the path. So I'm going to calculate the work along that piece, and then I'll add it to the work along that piece, and that piece, and that piece, so forth. Good? Okay. So let's jump over to Python and do this thing, like we say. Switching to computer. There I am. And Python trinket. Okay, so I don't have any there. So let's go ahead. I'm going to do one thing, and I don't really have to do this. Let's do this. Def. No, I don't want to do that. Let's just make our points. So I'm going to say I'm going to do capital A, is a sphere. Position is equal to vector 0, 0, 0. The radius is going to be equal to 0.05. That's fine. PB is the other point. It's a sphere. Position equals vector 1, 1, 0. And it will also have a radius of 0.05. Run it. I always like to run it after doing something simple. Okay, so there's point A, point B. Good. Okay, now I'm going to have just P. P is my point that I'm going to move. P equals a sphere. Position equals vector. Well, let's just say P is PA. Radius is 0.05. Color equals color.yellow. And make trail equals true. Okay, so now I'm going to need to pick my n. Let's say n is equal to 4. I'm going to use something large for it to begin with. We can always make it smaller. Now I'm going to say s is going to be equal to the vector b minus a. So it's going to be pb.pos minus pa.pos. So remember, pa is a sphere. Okay, but the PA.POS is the position property of that sphere. So that is that vector, A, whatever you want to call it. Now I can say dr is going to be s divided by n. This is one of the great things about Web v Python. I can do these vector operations. S is a vector. N is a scalar. I divide a vector by a scalar. It does it. So dr is a vector. I love that. Okay, that's just me. The first thing I want to do is just move my thing along and then animate it. So let's do this. Dr arrow equals an arrow. Position equals p.pos. Axis equals dr. Color equals color.yellow. Okay. So now I'm going to say while p.pos.x is less than pb.pos.x, right? Because I want to know when do I stop moving it? And I need some parameter. So I'm going to just look at the x value of my starting position and the x value of my final position. You could use y. You could use y. It'd work too. I'm going to put here rate 10. That way we can see it moving. We don't have to actually see it move, but I want to make it go slow. So rate tells it don't do more than 10 calculations, 10 loops per second. Okay, so the next thing I'm going to do is to, I said I'm just going to move it. Okay, so let's say, let's move the position. So I'm going to say p.pos equals p.pos plus dr. So dr is the step size, so I'm just going to move it along. And I think that's all I need to do. I need to move the arrow. So darrow.pos equals p.pos. I think that should work. And it didn't, because there's an error. Textures are not available for curve or point objects. I don't know what that means. Color equals color.yellow. Textures. Let's try this. Let's try just copying out this thing. See what happens. Textures. Okay, so that. See, I'm kind of eliminating finding out where that error is. So it's not there. Let's see if it's this. No. Okay. So it's got to be this. Can't find variable p. Okay. So it got down here. So this seems to be the line. It's a sphere. Position equals pa.pos. Okay. Okay, it moved one time. And that was it. Okay, cancel. Save it. Oh, I didn't save it as anything useful. That's fine. Line integral example. I'm wasting time. I know that. But I know what my error is. So dr arrow. Okay, we got it now. It's okay to make mistakes. There. So it moved along. Everything's happy. I'm trying to think. That's fine. Okay, so now let's, over here, I'm going to say work equals 0. Then down here, I'm going to calculate the force. F equals vector, what was it? What am I using? Y. So p.pos.y, p.pos.x times 2. And then 0. And then I need to find the little bit of work. dw is equal to the dot product f and dr. And then add that to my total. Work equals work plus dw. And then when I'm done, I'll print it. Print work equals work joules. Run. Okay, so I get 1.12. It should be 1.5, right? 3 halves. But that's fine because I had 4 4 steps. And you see what I'm doing? I'm assuming the force is constant over that step size. It's totally not. So let's just change this to 50. Oh, now it's going really slow. And you can't see the step size arrows because I turned it off. And I get 1.47. Okay, so I think in practice this works, and I'm pretty happy with that. Okay, let's go and do the other path, this up and down path. Let me save this. So let's go back over here and do the other path. Okay, so now we're going to do this path. So I need to break it into 2 pieces. I'm going to do this, and then I'm going to do this. So I actually have 2 line integrals. My f.dr is still the same. That doesn't change, right? f.dr is still going to be equal to y dx plus 2y 2x dy. It's still the same. Let's just do it along this path right here, though. So that's going to be, work 1 is going to be the integral from x equals 0 to x equals 1 of this y dx plus 2y dy. And now I do need to make some choices. No, this is 2x. I need to make some choices here. So what is the equation of this line right here? You know, this line was y equals x, but right here, this is y equals 0. That's the equation of that line. So I can say if y is equal to 0, then what's dy is equal to 0. So if I substitute that in, I get the integral of 0 dx, right? Because I substitute y is equal to 0 plus 2x times 0. And that's not too hard to do. It's 0. Okay, so now I need to do this integral, and I'm going to do it in the y direction. You could probably guess that was going to happen. So I have this. So let's say this is the equation x equals 1. Right, that's the equation of this line right there. So I have work 2 is the integral from y equals 0 to y equals 1 of y dx plus 2x dy. Now again, if x is equal to 1, I can plug that in right there. And I also can get dx is going to be equal to 0. Because if I take the derivative of both sides, the derivative of 1 is 0. So this term goes away. So I get 0 to 1 of 2. Now I'm not going to say x, I'm going to say 1 dy. So that's pretty easy. I get 2y from 0 to 1, which is equal to 2 joules. And then I have to say plus 0. Okay, let's go do this in our code. And I think it is useful to do it in the code. Now, I'm going to do the parabola, and the parabola code is a little bit tricky. I'm going to tell you the line integral for that is going to be tricky, but we're going to do it anyway. Okay, so let's just add our sphere in here. So let's just go ahead and make another sphere. I'll call it P2. P2 sphere, position equals PA.pos, radius equals 0.05, color equals color dot. If you want to change the color, you can. Make trail equals true. Okay. Now I need to break this into 2 steps, right? So let's just go down here. I'm still going to use that same in value. I'm going to say work 2 equals 0. I'm going to actually calculate the work along that first path, even though we know it's 0. Why know it's 0? Okay. So let's say dr is going to be equal to the vector. Well, it's going to be the vector 1, 0, 0 divided by n, right? Because I'm going to the point 0, 1 in the x direction. So now I can say while p2.pos.x, I have to do x because I can't do y. The y doesn't change. Is less than, let's just say 1. It is pb, but that's fine. 1. Rate, let's do 100. Now I'm just going to do the same thing as I did up here. So I'm going to do f equals vector p2.pos.x times 2 times p2.pos.x, so that's y. And then 0. No, aha! That was an O. Okay, and then I can calculate dw. dw2, well, I can just call it dw, doesn't really matter. It's going to be the dot product. Dot product's built into WebView Python. FDR. And then w2 equals w2 plus dw. Oh, and now I need to move the thing. p2.pos equals p2.pos plus dr. And I have a new dr, so that's fine. And then we can move the arrow. I didn't have an arrow. Don't worry about the arrow. Yeah, let's not worry about the arrow. Okay, now let's do the second step. So now I'm going to say dr is equal to the vector 0, 1, 0 divided by n, right? Because now I'm moving up. And other than that, I have the same thing. So I can actually just copy this stuff and do it again. And the only difference is, no, I need to do p. This is y is less than 1. That's the same. That's the same. Everything's the same. And then I can say print it. Print w2 equals w2 in joules. Let's see if it works. There's my first one. Very slow. Just getting it to move along a triangle is, I think, a win. And that one came out exact too. Winning. Okay, now we got that other line integral to do. It's a little bit more difficult. And then it is a little bit more difficult to program. So if you want to skip that part, that's fine. I'll do it at the end. So let's start again. So now we're going this way. Okay. And this is the equation of that line is y equals x squared. F is equal to the vector y, 2x, 0. And then dr is the vector dx, dy, dz. So f dot dr is y dx plus 2x dy. So now I want to integrate. The work is going to be the integral from a to b of y dx plus 2x dy. Okay, now again we have the option here. Okay, I could switch one of these dx's or dy's over to the other, so I could just get it all one integral, or I could do two integrals, and it totally doesn't matter. I feel like I'm just going to switch them over. Okay, that'll be more fun. So let's do this in terms of x. So I want to get everything in terms of x. So I know the y is equal to x squared, so I can put that in. So this is going to be equal to the integral. Now I'm doing x equals 0 to 1. And then instead of y, I'm going to put in x squared dx. And then right here I have plus 2x. But what's dy? Well, if y is equal to x squared, dy is going to be equal to the derivative of that, which is going to be 2x dx. So I actually have to put 2x dx in for that. So I get, let's say, 2x dx. That's my dy. So that whole thing becomes the integral of x squared plus 4x squared dx, which is the integral of 5x squared dx. So that's going to be equal to 5x cubed over 3 from 0 to 1. So it's going to be 5/3 joules. So it wasn't too bad. Okay. This is a bit more complicated. You know what? I want to show you the program I made, because I actually already made a program. And I think I normally would make the program, but this one, it's a little bit more complicated, and I don't want to waste a bunch of time. And I don't think it's that useful to rederive it. So I already did that. So here it is. Okay, let me make that a little bit bigger, so I'll now explain it. So let's just run this first. Because it turns out, and I did put the arrows here, it turns out it's not easy to break those lines up into paths. Let me show you what I did to break find my dr vectors, which I sometimes call ds. Okay, let me show you on paper what I do and why it's difficult. So suppose I have a parabola and I want to break it into 5 pieces or whatever pieces that you want. Let's say 5. So I'm going from here to there along this path. I can't break it into equal x pieces because that's going to make these arrows appear shorter, right? Or different size. It's not fair. It's not the same thing. What I want is this, and then this, and then this. I want it always ending on the line. So what I did is every time I make a step, I make an arrow like that, and then I just rotate the arrow up until the end of this arrow is on that equation, and then I stop it. And that's how I make all those arrows. I think it's kind of a clever little trick by me, if I do say so myself. But that's that. Okay, so let me go over some of the things here. I'm not sure what x and dx is for. Oh, that was just to draw the line. X and dx is to draw that parabola so I know where it was. This is the function to calculate f. I didn't do it as a function before, but here I did it as a function. This just creates the line. This just takes a point and moves it along a parabola to that last point and leaves a trail so that you know what happened. Then there's my p and my ds size. I'm not sure why I did that. D theta is how much the arrow moves every time when I'm trying to find where it should be on the path. And then, so I calculate it turns out that if I put a function inside of the dot product function, it was giving me an error. So I solved for the force as FTT, the temporary force. I drew the arrow for the force. I set the angle for dr to 0. And then this P tip is the point at the end of the tip. And then so I just move that up. I increase theta until that point is on the equation y is equal to x squared. And then I know where it is. Now I can find the dot product. I can find the work. And I get the whole thing. And I get 1.62. Let's say print. Let's just say, what did I say? It was 5/3. Is that 5/3 the same thing? Please say yes. Okay, that's the same thing. I mean, look, I only broke this into how many pieces? How many pieces did I break that into? 0.1. I just made the length 0.1, I guess. So, 10. So that's pretty good. Okay, so that's an example of a line integral. This is part of my classical mechanics course. If you've made it this far, which I don't know, maybe you left a long time ago, then it doesn't matter what I say. But I will put a link to the rest of my classical mechanics playlist down below so you can see the rest of the stuff, and I hope that helps.